Good morning, everybody. Welcome to today's lecture. I will present essentially one artificial intelligence technique nicknamed SISSO. But before I get there, I will introduce at least two different methodologies that actually meet into this kind of newer technology. And these two things are symbolic regression, and the name is almost self-explanatory, but I will talk to some detail into it, and compressed sensing is a technique borrowed from actually signal analysis, and people developing this kind of technique actually not even like to be called part of artificial intelligence. But still, in artificial intelligence and more specifically into machine learning, we have borrowed the terminology and some of the algorithms of compressed sensing. So let me start by saying that we are deep into this classification that I made last time, the part that is called representation learning of machine learning, and that's where I put also last time symbolic regression. So, as I was saying, we have on one side the so-called symbolic regression. It's by all means a regression technique. Last time I mentioned what we mean by regression, but I will repeat in a second. And the nice thing of symbolic regression, one of the many nice things, is that it also allows me to introduce an algorithm in itself called evolutionary programming, that uses inside it the so-called genetics or evolutionary algorithms that are used alone as a machine learning techniques, even though let's say they were used well before people called them machine learning, but they are machine learning. On the other side, a more mysterious thing that is compressed sensing, and you will learn about in due time today. The idea of compressed sensing is related to the idea of feature selection. That is one of the cardinal points actually of machine learning, especially if one wants to go into interpretable machine learning. And so these two kind of parents merge into this strangely looking algorithm nicknamed SISSO that I will present towards the end of the lecture. So you remember, I guess, what is regression, and in order to say what is regression, and introduce what symbolic regression is, that for the moment is grayed out in the title, I will go very quickly through other kind of regressions in order to pinpoint what are the differences between these methods and the so-called symbolic regression. So the general idea of regression is that we want to learn the dependence between some input parameters describing our data points, typically materials in material science, that is identified by the letter D, the descriptor. And you want to learn a mapping between this descriptor and a property of interest, some scalar properties, some formation energies, some band gap, and so on. And here I have not put one of the crucial points of last lecture, that is this irreducible noise that is what is not captured by the descriptor D in the property P. We know that exists, but it's of no use in this lecture, so I have not put it from the very beginning, but I thought that there should be a warning here. So one idea for regression, the simplest indeed idea, is linear regression. So one is just a scalar product between our descriptor and some yet to be found vector of coefficients. The scalar product of the two makes our property. Now a little bit of notation, because this comes popping up over and over. typically people, or some people, write this linear regression with a so-called bias term, hence the letter B, that is a constant term that does not depend explicitly on the descriptor. Not to be confused with the irreducible noise. This is something we can fit. But I will not treat that term, because with a trick it can be absorbed into the descriptor, and this is how you do it mathematically. So this term B is actually a 1 multiplied by some coefficient C0 that could be part of our vector C. Therefore, let's call the 1 as a D0 that is actually always 1. And then it's absorbed into the scalar product C. So just that you know that there is, if needed, a bias term there. And this is one possibility, a very simple possibility of regression, the so-called linear regression. What you do in linear regression, especially when you have a certain number of data points that is bigger than the coefficients that you have to fit, you minimize this kind of functional, so the difference between the property that you know and the prediction that you do from the model. You find the coefficient C such that this term here is minimized. In terms of matrix product, it's useful to see that, because I will come back a few times into this kind of representation. So the matrix D with components JL is this matrix here. This is our vector of unknown coefficient, and this is our known observation of the property, the PJs, and you want to fit this in order to get this as close as possible. Another, just a reminder, in this matrix form you would have that your D0 is always 1, and the C0 is here to make your bias. Another way to write the same thing in matrix form is this way, with this norm here of the matrix that is the same as this expression here, and is put here just to remind that this underscore 2 here is part of these P norms that are all written in this way. They will come back later, so I thought we should just refresh our mind on this notation. So back to the linear regression, and let me add another piece. That is another kind of regression that to some extent, actually to many extents, is still linear, in the sense that now we write our property as a function of the descriptor D for some point D as a sum over Gaussian functions that are evaluated, so that are centered on the data points. So the DI are the data points. Each of them is identified by a set of number that is the descriptor for that data point. So you have a Gaussian center there with a certain amplitude and some unknown intensity that is making the whole model. So what you see here is that here you have to fit these coefficients here, and in the kernel regression, as you will see to all depth in Santiago Rigamonti's lecture, you have to fit these coefficients here. Now there is another kind of regression that you will see later in the course, that is the celebrated neural network, and perceptron is a name for a specific kind of neural network. And don't mind the terminology. The idea here is to show that it's yet another regression with yet another ansatz for the model that you want to fit. So if you unpack this expression here, you have the scalar product of some matrix of coefficients. Now this has to be learned times the descriptor, that is the input. And this is passed to some nonlinear function. So let me show a bit in detail. So you have again a scalar product of some matrix W that has the terms of this matrix have to be determined in our algorithm for the training, and then you get a vector here that is passed to some nonlinear function that, for example, is an activation function like this. that could be identified by the arc tangent function. And then this is multiplied by another vector here of terms to be fit in order to get our scalar prediction P. So it is instructive at this point to kind of unpack this expression here and write down explicitly what is this for a situation in which you have, say, dimension 3 times the dimension of the descriptor 4 of this matrix here, and then again 4 terms here. So this corresponds of the neurons in the network, but you will see later in the course. What I want you to focus your attention on is this big expression here. That is to say, your neural network, this is a super simple neural network, at the end of the day is a kind of monstrous mathematical expression, as well as your kernel kernel regression expression is less monstrous typically than the neural network mathematical expression, and also this one is a mathematical expression. In all these cases, you identify specifically some terms, the coefficients in the vector C here, this vector of, again, coefficients here, and all these W terms in the two matrices that have to be fit. And in each case, you will see there is a specific algorithm to train them efficiently. But at the end of the day, you have a mathematical expression, and you have chosen the mathematical expression in order to have a somewhat easily solvable problem in terms of your unknown coefficients that have to be trained and determined in order to fit the data at best. Okay, but what if one allows for a completely non-specified, non-parametric functional form? Actually, one does not even want to have an idea on what functional form is explaining the data better, but the aim is that the functional form is found by some learning algorithm. Let's try to frame such a daunting problem. Let's say that you would have some property. This is a function of a descriptor. To fix a little bit the ideas, it is a function of some parameters that are of unit length and some parameters of unit energy, plus some constants of some other units. The reason I put explicitly the dimensionality is that I want to make a point soon about what can be combined with what in which way. But otherwise, let's say that you have D1, D2, D3, D4, so components of your descriptor. So you have an unspecified functional form that maps your descriptor into the property. And then you say, okay, how can I build functions that are mapping the property into the, so the descriptor into the property? You may say, well, I could have sums of at least two variables taken at the same time. And now I start with this kind of peculiar representation that is a tree. So the node of the tree is an operator that operates on the leaves. So now it's a very minimal tree, but you will see I can complicate it at will. And this is a useful way to represent this kind of regression. You may have the difference and then take the absolute value. And then you can define any kind of, say, unary and binary operators to be applied to our beloved input or subselection of the input. So this is an example of a unary operator applied to some length, and this is what is actually written in more usual mathematical formulation. And this is a more complex tree. In actually I've combined these two sub-trees with another node that is the ratio. So you take the numerator divided by this denominator and you end up into this expression here. And you will see in a second why this tree representation is very useful for this symbolic regression business. This is another idea in which you have a unary operator applied to a subtree and substituted here. Oops, I have that substituted. It is already revealing what is going to happen soon. But okay, you see that if I take a subtree away and I substitute another subtree that looks like a legitimate formula, I get another legitimate formula. That's a very crucial observation for symbolic regression. What do you do with symbolic regression? Well, at the end of the day, there is the usual business to try and minimize this expression here, that is our prediction minus the actual data that we have with the model square. The important point is the space over which we scan these functions here. So this is letter capital Phi, that just means the space of possible functions. I wouldn't say all possible functions. It's an attempt to explore functions that you can construct at least in this way and be as exhaustive as possible. And as you see with this tree representation in a very systematic way, especially in increasing complexity of the formula. By complexity, I have now used the word complexity in a kind of general sense, intuitive natural language sense, but you could start think that the complexity is related to how many nodes are in this tree, and indeed we end up with that kind of definition, or better, how many levels there are in the tree. So what do we do with this idea of constructing trees and then minimizing the formula that is the representation of what is shown in the tree? What do we do in order to construct a meaningful kind of expression and systematically progress towards a better and better expression? Well, we use what people call genetic or evolutionary algorithm. That is actually that exists independent of symbolic regression, and therefore I will now introduce it in a very general form and then particularize to the case of symbolic regression. So typically people kind of represent elements onto which symbolic genetic algorithm is applied as binary strings. So you can think that eventually everything is a binary string in a calculator. So you could have this as general as possible. Typically in the example, and I will use exactly the same kind of strategy. The fact that these are strings of bits is used in order to show what is happening to these strings. But let's say you can easily understand how this can be applied to specific cases. And to help you, I will show one example, and then I will come back to symbolic regression on how to represent things in a way that may be useful for, say, material science in general. So let's say that we have these strings of bits. Each of them represents some data point. And then importantly, we have a way to go from the string of bits to some kind of scalar function that we call the thickness function, something like an energy. And we are going to rank these input strings by means of their fitness. So here is like the highest fitness is the best, and I have ranked this kind of meaningless strings into some kind of ranking here. Then it starts a little bit of stochasticity. That is also what people think happens in nature. So roll the dice. Typically are a bit of skewed dice because I want to select candidates by giving preference to the fittest. And let's say that I have selected these two candidates. What do I do with these two selected candidates? Well, these are taught in the terminology of genetic algorithm as the parents that generate a new data point that is called the offspring. And how do I generate an offspring? Well, I mimic nature in at least in kind of genetic combination of parents. And first another roll of dice to decide where to cut the parents' genetic code, and then swap the pieces of the genetic code between the parents, and this would be two offsprings actually. And then I do another thing, it's called mutation. So I take just one of the offsprings generated, and I do something. Here I flip a bit, so I select randomly a bit to flip, and ideally I repeat this over and over. So I re-rank my input, my members of the populations, my data points, and I see if I have progressed enough. So if I have found something clearly better than the parents, and so typically need an external criterion to stop. Until I am not happy, I repeat and repeat over and over, and at some point I declare myself happy and I stop. So this is, as you see, essentially optimization procedure that is contains a lot of stochastic elements in order to produce new members of the population that are thought to be better. The idea is that if a parent performs better, good in terms of fitness function, changing something out of the parent is going possibly to bring an even better fitness for the offspring. So this, the underlying idea is that the mapping from the string of bits that is our descriptor and our fitness function is somewhat local, in the sense that one can fiddle a bit with the portions of this genetic code and improve a little bit the offspring. If the mapping was completely delocalized, so there is really a global property of the whole string at once, without possibility to partition into little, let's say, genes that contribute to our property, then this strategy would be as good as completely randomly changing the bits. So there must be some kind of locality in your representation in order to do this kind of manipulation. Let me show one example for, let's say, systems of atoms that people have used extensively in the past. As I was saying, way before this kind of business was called machine learning. And people had really, let's say, system collection of atoms, say clusters, molecules, even periodic replicas of this, so some crystals, say, with some specific configuration. And then, let's say, the crossover business was done by cutting by some randomly oriented plane the two selected parent structures, and then the hulls were recombined in order to give the offspring. So this is just to say that this methodology is well beyond the symbolic regression that I'm showing today. And how this is used for symbolic regression. So when you combine, when you use genetic algorithm for a symbolic regression, you enter what is actually called evolutionary or genetic programming. Programming is a general term to say that you get some input, from some input you go to some output, and the program learns how to produce the output by looking at the assigned labels. So you have some tree representation, you have selected, let's say, these two parents, kind of expressions, and then let's say how a crossover between these two parents can work. So then here the assumption is that the representation of our elements of the population in the genetic algorithm applied to symbolic regression is the tree itself. Why this works? Well, as I mentioned earlier, if you substitute a subtree with another subtree and all of the subtree involved are well-formed, refer to well-formed mathematical expression, then you get a new mathematical expression that is well-formed. So let's say you combine this part here into this. I put only one of the offspring here, and you get this new offspring that is the crossover between the two parents, and you can keep on doing this as long as you wish in order to get better expression. Now, if you continue generating expression in this way, and mind that I have not put in my examples the constant terms, for example, that of course will appear as a sum of these elements in the tree and then combined by means of products, ratios, and sums and so on with the variables themselves. So you get a bunch of this expression, and some of them will be reproducing better your output than others, because they are selected by means of this genetic evolution. At some point, you typically have the situation in which you get a bunch of expressions, and all of most of them reproduce properly your data. And in order to select which expression you want, you have a competition, or let's say you have to look at two things: how good is your fitness, and on the other side, how complex is your function. You may imagine that if you have two expressions that are equally good in yielding your training data, you would like to choose the one that is least complex. So we all know about Occam razor, and the idea behind the Occam razor, one of the main ideas behind the Occam razor, is that a simpler formula is more likely to generalize better, because it doesn't introduce probably artifacts that are there only to explain this particular data that you have used to derive that formula. Now, the concept here is the Pareto front. When you have more than one objective to optimize, what people do is to represent them in a high-dimensional plot. Of course, here is just two-dimensional. One direction for each objective. And what naturally happens is that there is a front, so a hypersurface here. It's just a line, it's called Pareto front, that is made by all those points, such that you cannot improve at the same time all the objectives with respect to that particular point. So let's say one point here, you cannot improve, let's say, both objective 1 and 2 from this point. So this is on the front. While, say, from this point, you can, so there are points such that either objective 2 or objective 1 are worse. So these are inside the front, and there is nothing outside the front. So this is purely empirical. There is no reason why this point is on the front or not. It could exist another point, but until you don't find it, this point here is the one on the Pareto front. So you have to discuss what happens there. So this is the explanation of the Pareto front. So the points such that there is no point that simultaneously improve all the objective functions. And then particularized to our symbolic regression, we have the so one target could be the accuracy, and the other target could be the complexity. That is really kind of evaluated in terms of the depth of our regression tree. So then at some point one has to decide where to select our point. There is no universal best solution on this kind of multi-objective optimization. Now you see why I drew the axis backward in the other plot, because of course the function that we want that we use is the complexity, but we want to minimize the complexity. So hence the Pareto front is on the other way. So like here there are functions that have a certain more or less constant accuracy, and say somewhere here this is the least complex for essentially the same accuracy. The same happen here if you are content to stop here in accuracy. So some people call this function parsimony in order to have the axis in the direction such that you optimize parsimony, but I mean I guess you can understand what's going on. I want to show one example of application of this pure genetic algorithm as I have explained it until now. So genetic programming applied to finding physical equations. So this was in this seminal paper in 2009, in which so after which also a code called EURECA was kind of made available in order to do this kind of learning of equations given the data. And one of the examples that is put in that paper is having this coupled oscillator system that was actually done experimentally, and this is it's kind of technical drawing representation. And what these people had as input data were the actual experimental observation. So the position of, let's say, this little mass here in the middle, and its velocity as well. Now here the target was actually to find what was constant in the motion, and the tree in itself was a bit more complex than what I shown, because there were also derivative in integration kind of operators, but I mean they are operators like any other. You can apply it symbolically and find your outcome. And what they found is let's say the Hamiltonian of this system, where the numbers come from the actual spring constant that were present. And the equation of motion. So you have this second derivative, or the first derivative of the velocity is related to velocity and position. And this was found automatically by the algorithm. There are many other examples in the paper, and you can find more other in literature. What I want to show is an example of a Pareto front that was found in this same paper for this double pendulum. So you see the parsimony here and the accuracy, and you have this idea that let's say if you define your complexity at a certain level, when you hit it, you take it the one that has the highest accuracy, or vice versa. You define your accuracy and you stop where you think the parsimony or complexity is the one you want, and actually these are kind of exact say invariants in the for this system that were found by the genetic algorithm. So this is very nice and powerful algorithm. The kind of drawback is that it is led by stochastic search, so you cannot you are not sure that you obtain the same result by repeating it over and over. But I want to make a point, a very strong point about symbolic regression. So when one is after looking for a completely unparameterized expression. Supposing that your exact equation is within reach of your searching algorithm, then it will be found, and this is the exact equation. Now, other machine learning methods with a parameterized kind of function, so the one you have seen, kernel regression, deep learning, you will see regression trees that this mathematical expression is not even continuous, so you cannot even write it in closed form. So this is not the case. Even if you give a very simple expression, it will try to fit it with all the power that the method has, and so it will probably overshoot in some sense. And in any case, you will not find a simple formula that might be shouting behind the data that you have there. So the idea is that also having not so many fitting parameter gives stability with respect to noise, in the sense that this, as we have seen last time, having a low complexity expression most likely does not lead to overfitting. Okay, so this concludes the idea, the description of symbolic regression, and then I start another part that is compressed sensing. So at the beginning it is completely unrelated, and then we will see how we merge the two parts. So I continue now so that you have both kind of literature method, and then I will present in a probably shorter second part the kind of novel algorithm that borrows idea from both the two already existing algorithms. So the idea of compressed sensing comes from signal analysis. Let's say that you have a observation in time of some phenomenon, unspecified. So this is its recording. I will tell what the red point and black point are in a second. But let's say this phenomenon goes like this in time. Now this time, function of time, one would like to extract the Fourier analysis of this, assuming that this is a periodic signal, because the purpose is to try and see if one can compress the signal, hoping that it has only few of the Fourier components active. So one samples the signal, and then makes a discrete Fourier transform in order to have the Fourier spectrum of the signal. And this is nothing else than a linear transformation, where the basis function are this exponential here. So the rows are the different frequency terms here, and the n here are the different. So the rows, sorry, are the different observations, and the columns are marked by the different frequencies. And of course, you want to learn the coefficient C. And let's say that this particular signal is found to depend only on three Fourier components. So it's actually a sum of three simple periodic functions, some sinus or cosinus. You see the red point here are the sampling point according to traditional signal analysis. And you see that you find out that most of the coefficients are zero for this particular signal. So you can express the signal by just using this Fourier component here. So this is typically done in signal compressing. Signal compressing means that you Fourier transform it and you pick up only the Fourier component that are above a certain threshold, and then on the other side you just go back to the time series by working out the anti-transformation. But this is compression after the sensing. The question that many people asked in the past is, could I also sense the signal in a parsimonious way, so that I don't have to sample as many data points as here? So if the signal is as large bandwidth, so in the sense that many Fourier components are active, this is typically not possible. But if the signal is sparse as this one, sparse in the frequency realm, then people ask why this is not possible. In principle, I could do fewer sampling, because at the end of the day, I have to fit only 3 coefficients. The rest are 0. I just have to find which are zeros. Okay, so let's say that now we want to sample the same signal, but we want to do fewer measurements, those that are needed to do the proper Fourier transform and the discrete Fourier transform. So the idea would be that you have a few observations, a lot of possible basis functions, and then you want to fit this vector coefficient here in the proper way. Of course, you see immediately a linear system like this one is underdetermined. So basically, you would have an infinite solution that yield the data. But now it is the crucial assumption. You know, or you suspect, that the signal is sparse. What sparse means that in this kind of representation, in terms of the coefficient C, is mostly 0. So most of the coefficients are 0, and only few are non-zero. This means, in this representation, I color the non-zero, that you are picking up columns in this matrix that is actually called the sensing matrix. And it turns out that you can write mathematically this kind of challenge, and this is this kind of norm 0 that I will come in a second. So the idea here is that I actually sample only the black points. These are the observations, and then I reconstruct exactly the signal with much fewer observations than for the whole, if the signal was not sparse. Of course, one has to suspect that the signal is sparse, but one can also check afterwards if the signal was sparse or not. So let me dig into what this quasi-norm 0 is. First of all, it's written in the same way as the other ones, and this p is now 0. It's like taking the limit when p goes to 0 of this norm. If you think a little bit about this, and I will show in a second also a graphical representation, this boils down to the number of terms in the vector that are different from 0. So this is the reason why there is a 0 here. This is not a legitimate norm. It breaks some of the rules, one specific rule of norms. It is the triangular inequality. But nonetheless, it can be taken as a limit of these p norms, and it's written in this way. Before I show a little bit more about this 0 norm and its evolution, let me go to another concept that is related to compressed sensing. As I have shown here, the problem is actually related to picking up columns from this sensing matrix here. Compressed sensing became a little bit used in machine learning recently because of this capability of extracting features from a large set of candidates. So this is vital in machine learning, because typically you have candidate features and you don't know which ones are the actual good features. So you have on one side the feature selection, that is this extraction, and I wanted to make this distinction with another concept that is feature extraction, that is sometimes confused with the feature selection. So this feature selection is really selecting some of the features, and it can be done in few ways. One way is the so-called greedy selection, that is basically applying some kind of filters, and each feature with the property of interest. Then you have search strategies like genetic algorithm. You see that things are starting building together. Or you have attempts to write analytical optimization functions that one can actually optimize in a non-stochastic way, and these are called the embedded methods. The feature extraction is another concept in which features are, yes, reduced from an initial set, but they are typically combined. So possibly all the features that you give are combined into fewer features. And this is the realm of dimension reduction that you will see present in the unsupervised learn lecture, and the autoencoders, for example, that will be briefly presented also in the neural network or deep learning kind of lecture. Wrapping up the first part, and for the compressed sensing idea, I arrived at this expression in which we want to solve this linear system with the condition that the vector C has as few linear, so non-zero terms as possible. And therefore you have this competition between having a small error and having also a small vector C representation. So non-zero vector C realization. Of course, if you have as many coefficients different from zero than the number of observation p, you end up in your usual determined linear system, and then you go to an overdetermined, so you have your usual regression. But here the idea is that the C is to be as small as possible, hence your error will be more than zero. So the compressed sensing historically started, let's say, in 2006, when people realized that this thing here could be mapped into another problem that has actually the L1 norm. Why this was important? One step back. If you write the expression in this way, the only way to solve exactly the problem is to enumerate all possible solutions where one coefficient is different from zero, two coefficients are different from zero, three coefficients, and so on and so forth. So this is combinatorially explosive, and it turns out that there is no exact algorithm that is faster than this enumeration. So this belongs to the class of the so-called NP-complete problems. So you cannot do it better than that. But you can solve it approximatively if you actually go to this other problem here that has as regularizer the L1 norm, so the norm where this index is 1. This norm is this one, essentially. So the P is 1, so it's the sum of the absolute component of the vector. And so to get an intuition on what's going on here, the kind of balls in at least in 2 dimension related to the norms as a function of p are the familiar Euclidean norm is the familiar circle. With p equal 1, you have this square here, 45 degrees turned. And when p is smaller than 1, you see that you get this spiky object, and then you understand why if this goes to 0, you get essentially a star here that is the exact sparsification that one could be looking for. On the other side, if you go towards infinite, you get this other square here. Because so if you think about for a moment, when p goes to infinite, you get the maximum component of the elements in the vector. Now, this observation is useful because suppose that you have found a manifold that is the solution of this part of the problem here. So manifold because we have said that we have fewer rows than columns in the matrix, that means that you would have a linear manifold that solves the problem. So this linear manifold would look like this, for example, in only 2 dimensions. If you look for the one solution that is on the manifold that minimizes the L1 norm, would mean that you make the intersection between this manifold, it's just a straight line in 2 dimensions, with this ball in L1 norm that hits the manifold on one of the axes. So this is not by chance. With the L1 norm, this kind of ball that is not smooth will touch the linear manifold that could be the solution of your problem, typically on the axis. And this is why this L1 norm is also yielding solutions such that most of the coefficients in our solution are 0. Okay. There is a condition that was found such that this property actually holds, that is related to the number of features, so the number of columns in your matrix and the number of observations, that is m. And you could find a proper solution with this L1 regularization when the number of features is bigger than a constant times the logarithm of the number of features. So the important thing here is the relationship between the number of observation with the logarithm and the number of features. So it means that by changing a little bit the number of observation, you can go to much number of features such that you still get a good solution to this problem. Okay, ready to wrap up. The compressed sensing that is also called sparse recovery is a technique that enables the recovering of sparse signal from very few non-adaptive measurements. So I have not talked about non-adaptive because it could be understood only now. So essentially, you do not have to say I sample one or few data points and then I see if I am converging my series expansion or not. This is a set of data points that you can design beforehand. In the case that I will show later, and they are typically useful for data science, for material science, we do not kind of design which observation we do. We have the observation. But it turns out that what you need about this observation is that they are uncorrelated. The point is, if you do the typical Fourier transform, this observation have to be equally spaced in time, while the observation that you do for compressed sensing should not be equally spaced in time. Now, in situation where you do not have time, this is a little bit more vague. The point is that you should have data points that do not carry the same kind of information. And then you can hope to use this compressed sensing technique for doing your learning. Okay. Essentially, I will actually close here, and I'm ready to take questions for this first part. You will see how this compressed sensing is going to be merged with the symbolic regression. But let me just close by saying that compressed sensing by itself has been used in material science, and in the slides that I will upload, I will put some reference of people that have been using some kind of vanilla compressed sensing in order to find good models that have been proved to be useful in material science. So for the moment, I thank you for your attention.